Okay, time to start. Our next speaker is Danylo Radchenko. It is a member of the probably the most famous team in discrete math and around that, right? And there's a already proved in the distance taken in dimension 24 and several other. It is as I and also universal optimality of dimension 8 and 24 that is expected result. And so, okay, let's start.
Yes. Okay. Thank you, Oleg, for inviting me to give this talk. So, as you've mentioned, I will talk about universal optimality, and I will talk precisely about the results in dimension 8 and 24. And I mean, of course, it's kind of for this audience is maybe a bit too simple, but I'll start with some basic motivation. So, and the motivation is to kind of study nice configurations of points, but like not on compact space, but in the Euclidean space RT. And for the purpose of this talk, I will only consider the problem of minimizing potential energy, which for some reason gives very good measure of goodness for configurations. And so in principle, if the configuration were finite, you could just define the potential energy as the sum of all pairwise interactions, where each interaction it depends only on the distance between the 2 points, and the distance is always the Euclidean distance. And of course, this kind of breaks down if you work with infinite sets, which is kind of what we want to do. So there's something one needs to do with the double sum to make it work for nice potentials. And also, if we want to minimize this quantity over a set of configurations, like if you allow configurations to spread out, the energy will obviously decrease. So we want to also control the density. And this is done by somehow not very exciting, but like not so difficult definitions. So the right way to renormalize the energy is actually not to consider all pairwise interactions, but to consider like the average value of all interactions with a fixed point, and then average over points in the configuration. And the technical definition is given in this formula. So you basically take all interactions in a large enough ball and then renormalize it by the number of points and let the ball grow to infinity. And the second definition is how to deal with the escaping to infinity problem, which, well, you just consider only configurations which have a finite density between 0 and infinity. So by density here, I will only talk about center density because it's somehow more natural to work with. So it's the average number of points per unit volume in a large enough set. And so the problem, kind of more rigorously formulated, is, well, given a potential function, we are interested in finding all the minimizers, global minimizers of the energy with respect to that potential function, over all sets of this density 1. And there's like some scaling game involved, but it doesn't really matter. If you fix density 1 once and for all, it works. And then if we're really optimistic, we also want to describe all such configurations. And of course, this is kind of a very difficult, hopeless problem. It's related to certain questions of material science, which are also very difficult. It's not quite correct to call this a version of crystallization problem because it only accounts for some. It doesn't account for many physical effects, but it's kind of a good approximation, first order approximation. And the crystallization problem is just a question about why do crystals form at low temperatures? And in a sense, it's related to this, but I mean, it's not precise. I mean, there's no direct connection. So one needs to make the problem about energy a little bit more physical to make this connection correct. But I will just talk about the mathematical problem. And so there are certain potentials which are more natural than others in some sense. So one is the hard ball potential, which is kind of a very boring one. It just measures whether the particles are close enough or not. And so this parameter capital R here, it corresponds to the size of a certain imaginary ball that you imagine around each particle, around each point. and the two particles interact if these two balls overlap, and they don't interact if they don't. And as I'll mention after that, it's related to the sphere packing problem for obvious reasons. So next, there's the Riesz potential, which for certain values of S, it appears in physical context. So it's just a power law, inverse power law. And then there's the Gaussian potential, which corresponds to something called the Gaussian core model, which, as far as I know, doesn't really correspond to any physical interaction, but it's useful for approximations. And it turns out to be very natural and useful for the problem of studying energy, more precisely about it, for the universal optimality phenomenon. But I will talk about this later in the talk. And so going to the first potential that one can study, when we're talking about hardball potential, the minimization problem is the classical Kepler problem or the sphere packing problem. And one can kind of make an alternative formulation, which is maybe a little bit easier, but it's essentially the same thing. So we keep the notion of density from before, and then we introduce the packing distance, which is just the minimal density between the points in the configuration. And the question is, well, you want to either fix the density and maximize the packing distance, or vice versa, fix the packing distance and maximize the density. It's these two things are equivalent up to scaling, and they both lead to the same problem. And on this, I'm pretty sure everyone knows this already, but I will just list the known results, which are very few of, and I will concentrate on the full problem. So the problem is no restrictions on the configuration, so full space of configurations in d-dimensional space, and whatever the best sphere packing. So for certain restricted classes, there's more known. That maybe we'll mention a little bit, but not much. So in dimension 1, the problem is kind of boring. In dimension 2, it's long known. I mean, it's in the case of lattices, it's the theorem of Lagrange from 1770, I guess. But for arbitrary configurations, there's some sequence of more and more rigorous proofs going from Thue to Feestot from 1890 to 1940. And I'm pretty sure I'm kind of forgetting some people who did something more. I mean, there's other people who gave rigorous proofs in between these two dates, but I'll kind of, I either don't remember them or don't know them. And in dimension 3, this is a much more recent work of Tom Hales. And then there's two dates here. So one is for his original proof, and the other is for the computer verification of the original proof. So, and there's a long story related to that, but I won't go into that either. And then there's a huge gap. So the next dimension where the precise answer is known is 8. And this is a breakthrough work of Maryna Viazovska from 2016. And then like a short time after that work, we managed to do the same thing in 24. And you get another huge gap where no precise results are known. So I've omitted several things. So in dimensions up to 8, there is a good guess for what the answer should be, as well as in dimension 9, although I'm not sure like to what kind of certainty to put on these claims. So I think in dimensions up to 8, it's pretty safe, but dimension 9 is kind of strange. And as far as I know, in dimensions maybe 11 and higher, there's no good guess except for the Leech lattice. Dimension 10, I'm not sure. I think there are some candidates, but maybe not. No, I'm not sure if anyone believes they're optimal. But in any case, this is the full list of rigorous results, and they kind of break down into two groups. Well, there's a trivial group which kind of falls into both, but we ignore the dimension 1. So dimensions 2 and 3, they're kind of based on local analysis arguments, and dimensions 8 and 24, they're based on, I'm calling it Cohen-Elkis linear programming bound. It's not, I mean, there was some related work by Dima Gorbachev. So the linear programming bound is perhaps not their invention, but they were the ones who found the 8 and 24 were kind of close to being optimal by linear programming methods. And then this is exactly what was proven by Maryna in dimension 8 and by the same group of authors in dimension 24. Okay, so then if you talk about other potentials, so if you talk about the Riesz potential and the Gaussian core model, the problems are not, well, they're not unrelated, but the general energy minimization problem is much harder than the sphere packing. So what is known is kind of some, I mean, there's a lot more known, but just two simple observations is if you can prove, if you can prove that some configuration is optimal for all Riesz potentials with parameters sufficiently large, like it, yeah, then there's a simple argument that shows that it has to also be an optimal sphere packing, and the same is true for the Gaussian potentials. So in principle, if you want a solution to this problem for all parameters for like a large class of Riesz potentials or Gaussian potentials, it makes sense to only consider the cases where we know the optimal sphere packing. So if you look at the two-dimensional case, I mean, the two-dimensional sphere packing is actually quite easy to do. Well, okay, relatively easy to do. And it's known for a very long time. And for the energy, the problem is actually much harder. So it's not known for any value of S that it's optimal for Riesz potentials, but it's widely conjectured to be the case. And what is known is, well, there's a pair of related results. So one is due to, it's a series of papers starting from Rankin to Cassels to Diananda and Enola, that A2, among lattices, the A2 lattice is optimal for the Riesz potentials. And then there's a related result of Montgomery that shows it's also optimal for Gaussian potentials. And these results are kind of, I mean, they show that A2 is a good candidate for universal optimality, but in general, it's not really expected to be very often the case that you have some universally optimal object. And it's, I mean, it's actually expected to be very rare. And then in dimension 3, it's kind of it fails very badly. So you have lots of, the dependence on the potential is actually quite complicated, even for lattices, as far as I know. So in this like two-dimensional conjecture, I mean, it has something to do with the Euclidean space, and one might ask if the curvature of the space has anything to do with the with the optimality, and in certain sense it doesn't really matter. So because we're somehow talking about the leading term in the growth, and there's a result, a nice result by Hardin and Saf. I mean, the result is much more general, but I'm kind of want to present it in this context. So they're talking about the energy minimization with respect to Riesz potentials for finite subsets of some surface with fixed measure, which we fixed to be 1. And they showed that there is some universal constant for which there is a growth, the energy as you increase the number of points grows exactly like n to the power 1 plus s. And this universal constant, if we knew the answer to the conjecture on the previous slide, would be the value of the, well, either Dedekind zeta function or Epstein zeta function. It's kind of, it's the zeta function of the A2 lattice. Okay, but yeah, it's not, I mean, it's not particularly deep think. So what, I mean, the complicated part is actually showing that the A2 lattice is universally optimal. Once you have that, I mean, this is kind of easy to prove. And they have some nice pictures. So this is the conjectured, well, I don't know if it's kind of hard to conjecture any global optima for energy, but it's a good representative of what the global energy minimizer on the sphere is for 400 points. And there are, I think, 2 different configurations here. And in both cases, you see there's large patches of A2 lattice kind of glued together with some singularities, which come from the fact that you can't really do the flat, I mean, you can't really arrange the A2 lattice completely on the sphere because of the curvature. But somehow, like for the energy minimization, it really doesn't matter because you're talking about the leading term. Okay, so and there's also this picture that I like from real life. So these are some, well, I actually don't know much about this stuff, but so these are so-called Abrikosov lattices, which are lattices of some superconducting vortices in superconducting metals in magnetic field. And these are actual photographs from electronic microscopes. So, and there's a conjecture of Abrikosov, which more or less would be a theorem if one also knew the universal optimality for A2. So, which precisely describes the behavior of these vortices. Okay, so I was kind of talking about universal optimality without defining it, but it's very clear roughly what one wants. So a configuration, and this is definition, I guess, going back to Cohn and Cohn and Kumar. So configuration is called universally optimal if it minimizes P energy for all completely monotone functions of squared distance. And there's a little bit, maybe not so natural notion, but actually it's kind of nice, and it includes all completely monotone functions of non-squared distance, just of distance. So we kind of just enlarge the space of completely monotone functions. And so both examples that I gave before, Riesz potentials and Gaussian potentials, they are completely monotone functions of R squared. And there's a result, the old theorem of Sergei Bernstein, that tells you that, I mean, it's not formulated in this language because I'm talking about completely monotone functions of squared distance. But when we reformulate it in this language, it tells you that Gaussian potentials span the cone of all such functions. And there is a precise notion of what it means to span, but basically any such function can be written as a like integral of Gaussians with respect to parameter, with respect to some Borel measure. Okay, so Cohn and Kumar, they gave a kind of conjecture which is better than what I'm giving here, but for the moment I will say it this way. So they conjectured in dimensions 1, 2, 8, and 24, the configurations given by these nice lattices, so Z, A2 lattice, E8 lattice, and the Leech lattice are universally optimal. It's actually not the conjecture they made. They made a much better conjecture, but I'll explain it in a moment. And they also proved that this conjecture is true for dimension 1, which is actually a non-trivial theorem, unlike the sphere packing problem, for example. So it requires some work. So to explain what the direction conjecture was, I have to talk about linear programming. So with the usual notation for Fourier transform in d dimensions, there's a theorem which, I mean, it's a successive sequence of theorems, really. So there's a Cohn-Elkies LP bound for the sphere packing problem, which I think in the special cases was formulated by Dima Gorbachev. And there's then the Cohn-Kumar problem for the energy minimization problem. And they're kind of, I mean, the way they work is almost the same. And once you have the proof for the sphere packing bound, it's kind of almost trivial to make it into a general upper bound for the energy. Sorry, lower bound for the energy. So the claim is if you can find a nice auxiliary function, f, which lies below your potential, but which is positive definite. So whenever you have such a thing, you can get some bound from a clever application of Poisson summation formula. And I will actually give this proof. I think I have enough time. And the bound only depends on the values of this auxiliary function at 0 and its Fourier transform at 0. So let's assume for simplicity that the configuration we're talking about is periodic. It's not strictly what I was talking about before that, but it doesn't really matter that much. So you can always approximate things by periodic configurations. And it makes the proof much, much easier. So there's a more general version, which is actually not in the original paper by Cohn and Kumar, but I won't talk about that. So, and the argument is kind of nice. It fits on one slide. And it's actually important for the like sufficient conditions, so I give it here. So if you apply the Poisson summation formula to this auxiliary test function, which we assume to be Schwarz for simplicity, it doesn't have to be, but it's kind of convenient. So we start with this identity. And with this, so basically we start with the definition of the energy with respect to the potential P, except that I'm simplifying I removed all the limits because one can do the summation directly for periodic sets. It's just an average of n squared different values. And then for each inner sum, the sum over the lattice, we basically apply the first condition that the potential is at least as big as the value of f. The value of the potential is at least the value of f at the corresponding point. So now in the original sum, we didn't have summation over 0 because p wasn't defined there. Now f is well defined there, so let's add this back. So we basically get the same sum, but now with no restrictions on x in the inner sum. And now we apply Poisson summation formula to the inner sum and rearrange the terms of the outer sum and put them together. And that gives you contribution. So minus f naught, we keep it from before, plus these are the terms coming from the Poisson summation formula. And when we rearrange the double sum, we actually get something which is a square of a trigonometric polynomial, which is non-negative. And then you just drop all the terms except the 0 term. So you get the bound as claimed before. So what's very nice about this proof is if you, you might be very lucky that actually these inequalities that you use here, the non-strict inequalities are actually qualities. And it's easy to tell what one needs for that. So if you think of the configuration C, let's just say it's a lattice. So we want to prove, if you want to prove that the lattice is optimal for some p energy, it's actually sufficient to find an auxiliary function for the LP bound. These are the conditions for the LP bound. If these conditions are actually achieved for the points of the lattice and for the dual lattice, then if you just work through the proof, it tells you that the energy of the configuration lambda or C actually agrees with the lower bound. So you automatically get, you kind of find the minimizer for free. Unfortunately, that usually doesn't happen for isolated P's, as far as I can tell. So what they have conjectured is in dimensions 2, 8, and 24, this actually should work for arbitrary, for all potentials, or for all potentials with this complete monotonicity property. And in particular, because of this density result of Bernstein, it's enough to establish such results. So if you expect that all potentials are going to work, it's actually enough to work with Gaussian potentials, which turns out to be important for this problem, for at least the way we solve it. And this is basically the main result. So we proved that the E8 lattice and the Leech lattice are universally optimal in dimensions 8 and 24. And so we confirmed the two cases from the conjecture of Cohn and Kumar, but not the two-dimensional one. So I will say a few words at the end about that, maybe. So, and just to remind you what the E8 lattice is, it's just this formula. So it's all integer or half integer vectors with sum of coordinates divisible by 2. Both the E8 lattice and the Leech lattice are even unimodular. In particular, they have all norms of vectors in them are square roots of integers, which is actually the only thing that we'll use, the only two properties that we'll use about the Leech lattice and the E8 lattice, except in the case of the Leech lattice, you also need to use eternal roots. So no vectors of length square root of 2. And so the point is, if you look at the sufficient conditions for the LP bound, and you plug in lambda to be the E8 lattice, it tells you, if your function f is also assumed to be radial, it actually tells you, because of these equality conditions together the inequalities, it tells you the values of the function and the first derivative at all these points. I mean, it doesn't tell you, but if you want to find the function, then you have to also satisfy certain equality conditions, which seem quite restrictive. And actually they are very restrictive in the sense that we prove that these conditions for an arbitrary Schwarz radial function, they completely recover the function. So, and this is the main technical result, kind of the main novel idea in this paper, that there's like some interpolation formula, an analog of polynomial interpolation in the Schwarz space, which is quite a bit more complicated, which is perfectly suited for the linear optimization, linear programming bound. So there's certain explicit expression which allows you to reconstruct the function, any function, from the values just at these points. Okay. And you can kind of see that it's relevant to our problem. And what's a bit surprising about this thing is the proof is actually, it relies on the theory of automorphic forms. So, and the whole the whole idea of such a formula, if you reformulate it in a sufficiently, in a suitable way, it actually naturally has an interpretation in terms of modular forms. And we kind of use this fact to a very large extent. I mean, the whole proof is based on certain arithmetic properties, and it's kind of a nice feature and the problem with this approach, because we can't have too much freedom in choosing these numbers. So it has to be square roots of 2n for this thing to work. And the functions, so everything is explicit here. It's just kind of messy to write down. And so if you go back to the question of universal optimality, so what happens is it's kind of, I'm condensing large chunks of the paper, which is 90 pages long, into one slide. So what happens is you use this theorem to find an explicit candidate for the optimal auxiliary function. And in the end, if you kind of suppress lots of things into some notation, it takes the following form. So somehow it's the potential you start with. So I'm only talking about the Gaussian potential. So it's the potential here minus sine squared, which is non-negative, and actually it has some nice vanishing properties at the points square root of 2n, times the Laplace transform of a certain kernel function. And this kernel function is a terrible beast. It's, I mean, there's an explicit expression in the paper, but depending on how you choose your notation, it takes about between like maybe 4 lines and half a page for the E8 lattice and maybe several pages for the Leech lattice. And it looks completely random. So what's nice is, I mean, it could still be a very hard problem to actually prove the inequalities for this object. But what happens is the kernel itself turns out to be positive or non-negative. So this kind of saves the whole thing. Otherwise, I think it would be perhaps too difficult still. So what happens is the kernel itself is non-negative. And once you prove the non-negativity, well, you automatically get the upper bound for f. So f would lie below the potential, because this is a potential and this would be some non-negative term, which we subtract. And on the other hand, there's a duality argument, which I won't go into, but it's basically based on the Poisson summation formula that tells you that the opposite inequality with the Fourier transform also follows from the same property. So this is true. So you just need to prove this inequality in 2 variables, and the function k is actually a completely explicit function. There's a change of variables one can do, which expresses it in terms of polynomials in the 2 variables and elliptic integrals of like first kind, like the elliptic E integral and K integral, and also logarithms. So it's some explicit elementary, well, somewhat elementary function, which we have no kind of good interpretation of. So we can't really interpret this inequality in a nice way to give a clean proof. So what we did is we actually proved this using using interval arithmetic. Okay, and that's kind of, I mean, it's the end of the story modulo all the details. In the 24-dimensional case, there's some additional difficulties which are related to the fact that this integral here actually doesn't converge for all values of x. There's a singularity. So it's kind of, you can still define the function in a nice way, but there's a lot of complications arising. And also, and in the end, it ends up, so this inequality is not enough, one needs something more precise. But I really don't want to talk about that. So I want to say a few things about the 2-dimensional case. So this approach that I outlined is actually, so in a sense, it uses very little information about the lattices, but actually the kind of information that it uses only happens for even unimodular lattices. So it kind of doesn't help because A2 is not. So what happens is we kind of, I mean, one can imagine, let's be optimistic and try to see if a similar strategy might work. So then one would need to interpolate from the values not as square roots of even integers, but at these numbers, because these are the only numbers from which, for which the sufficient conditions tells us something about the auxiliary functions. And this sequence of numbers is density, has natural density 0 among integers. So in the paper, we conjectured that actually the interpretation doesn't work, which is a kind of a very, I mean, it's a non-trivial conjecture, but somehow we all knew the answer was that it wouldn't work. And now there is actually a rigorous proof. So Nasser Sardari recently shown that there is an infinite dimensional space of radial functions which vanish to second order on this set. So actually there's no hope of doing interpolation the same way, which tells you that there probably isn't a single good candidate for the LP bound. But on the other hand, there's some numerical evidence that actually the space of solutions for that should be infinite dimensional. And there's even some kind of semi-arithmetic things which are going on. So there's a way to embed this nasty sequence into a union of arithmetic progressions, which at least when you do some computations on the computer produces auxiliary functions which satisfy the right inequalities. But there's certain like nasty arithmetic effects which make the whole thing work very badly with the modular form approach. So we kind of have some numerical evidence, but nothing rigorous. And it's kind of, yeah, I would say it's kind of far from any rigorous proof. But at least there's some hope. And there's another thing that I want to maybe briefly mention. So if we look at this LP bound and the optimization problem, so it seems to be there's something very strange going on. It's more of a Fourier analytic nature, but I still want to mention it. So if you just try to make the best bound for the energy for Gaussian potentials in d dimensions, and that basically for the LP bound this means this, and you try to solve it numerically, so we actually make some precise conjectures in the paper. So as long as the dimension is at least 4, there's some strange phenomena happening below that, so which we don't really understand. It seems to be there is a unique optimal solution to that problem, and it's actually a nice radial Schwarz function. And moreover, the points where this bound is tight, so where the upper bound is tight, is a certain discrete set of radii, and these radii actually grow like square root of 2n, so the same way as in the nice case. And the condition actually for the Fourier transform happens for the same set of values, which is kind of non-trivial. So there's no obvious reason why this should happen, and we don't really know an explanation for that, except in the cases where we actually know the precise solutions, which is 8 and 24. And also it seems like there's a similar interpolation formula recovering anything from these values. So in principle, if you kind of don't want to prove universal optimality, but just want to find the optimal LP bond, there's something strange and mysterious going on. And it's somehow very non-trivial from the Fourier analytic point of view. I'm not sure if it's the best approach to kind of improve LP bonds in high dimensions, may not be. But on the other hand, like the behavior of these objects as dimension increases, which one can even take to be a real number. So there's actually a way to reformulate everything not for integer dimensions. So and then everything seems to behave nice and smoothly with D. So there's maybe some hope that if one could analyze this problem very well, one could improve on the LP bounds for this re-breaking problem. Okay, but I think we went over time, so let me stop here. Thank you.
Thank you very much. Thank you very much. Very interesting. Very interesting talk. Questions, comments. Oh, I did prove already that D4 is not universally optimal because it is proved for locally, right? But what about the global? Do you have some?
No, well, I don't, but there is, I'm kind of like from talking to several people, I got the impression that not everyone is kind of aware of current developments. So there is a paper with, I think, Cohn, Kumar, and Hill Schurman in the Physical Reviews. I don't remember exactly the journal, but what they do some numerical experiments with this problem. And specifically, as far as I remember, in dimension 4, they're claiming that universal optimality of the D4 as a lattice should still be true, even though the local, like the
okay.
the root system,
Is it possible that locally is not universal optimal, right?
Locally it's not, yes, but
it's not universal optimal.
As far as I understand, the expectation is that the D4 root lattice is universally optimal in the Euclidean space. But it definitely is not achievable through LP bounds, obviously. And the numerical evidence shows that it's true. I'm not sure if it's rigorously known, but no one expects it.
Okay, but I don't understand.
Probably
that means, is it possible to prove that the D4 is the best packing using this technique? What
yeah, well, that's true. And I'm not sure if it would be easier.
Wow.
No. But yeah, at least people expect, and also something from the same paper is that in dimension 9, there's this family of kind of liquid diamond packings that Conway has constructed. And for some value, it seems like this, I'm not sure, I feel like this is a very crazy conjecture, but they're claiming that it could be universally optimal in dimension 9, which is also, it also cannot be LP optimal, but there's at least some evidence that there's another universal optimal.
Okay. It's for me, it is very strange that it works in dimension 4. I mean, this. And do you know that recently, just his name, Anatoly Demarsky. Do you know this name? Demarsky.
No.
He's from Skoltech. He sent us recently a message to Abrikosov, but he's a physicist, and he actually he uses a very similar technique as you. Right. Okay. If you're interested, he'll ask maybe to some workshop. He's looking for. Maybe we can organize. If you're interested, we can invite him. But he said that the physicists also familiar with this technique. They never use like some different terminology, but in different context. But however, they work in that. Okay, more questions, comments. Thank you very much. Now we have a break, 13 minutes.